Yep.
Okay, let's go.
Okay, great. All right, just quickly, I'm John Tomsick. I'm going to be chairing what is an afternoon session there, although it's 7 in the morning here in California. Our first speaker will be Abby Stevens, and she's going to talk about time series exploration with Stingray.
Thanks, John. Hello, everybody. It's morning here in Michigan. Happy time, whatever it is for you. Yes, I'm going to be talking about time series exploration with Stingray. I am presently an astronomy instructor in the General Science and Integrative Studies program, and I have a paused NSF Astronomy and Astrophysics Postdoctoral Fellowship at University of Michigan and Michigan State University. So, briefly, even though you've been seeing this already this week and you're going to see more of it the rest of the week, features in X-ray light curves, or why we would want to look at time series. We have coherent pulsations from neutron stars. This can include burst oscillations, spinning up and spinning down. The pulsations don't always stay the same. Glitches in the neutron star pulses, and transitions or switching from, for example, X-ray pulsations to radio pulsations. We also have, for black holes and neutron stars, we have quasi-periodic oscillations, or QPOs, which you've been hearing about. There are two general camps: low frequency QPOs. There are a few different ideas for what they might be. For example, the precession of a corona or hot inner flow, or magnetic warps in the accretion disk that are slowly moving throughout. There are also high frequency QPOs, which could be possibly hot blobs in Keplerian orbits at the inner edge of the accretion disk, or radial oscillations in the boundary layer of the neutron star for the high frequency neutron star ones. We also have broadband or band limited noise at about less than a hertz. So in the plots down here, we have two types of QPOs, which are the big peaky bits. And then the red curve has quite a bit of broadband or band limited noise that the QPO is sitting on top of. Also in this high frequency QPO, we see that there's quite a bit of low frequency noise as well. And when we're looking at X-ray time series, the basis for all of our exploration happens with Fourier transforms. And this is because we have evenly sampled data and evenly sampled light curves in X-rays, because there is such thing as having zero counts for counting our individual photons. So I wanted to show this GIF briefly that I really like for breaking down Fourier transforms to study the time domain in the frequency domain. This breaks down our light curve into the component sine waves and takes the amplitude of each sine wave of the sines at each frequency. And so in this way, our Fourier transform at the bottom can tell us about the light curve information in the time domain. Now, as we are using time series exploration, the tools that we have in, for example, Stingray, make it clear whether or not you need to have evenly sampled data to carry this out. Because in things like optical photometry, you might not necessarily have evenly sampled data. But it's not just X-ray data that are interesting in the time domain. On the right here, it's a screen capture of the recent papers that have cited our Stingray paper. And you can tell all of these people have had significantly more productive pandemics than I have been having so far. Alex Tedorenko et al. Published a paper on multi-wavelength fast timing in radio, submillimeter, optical, and X-ray. They were using Stingray for that. John Pace et al. Were using Stingray to look at optical and X-ray lag, so multi-wavelength multiband lags. Kimura et al. Were looking at power spectra of dwarf novae in a cataclysmic variable, SSSIG. So Stingray is being used for looking at white dwarfs. I know that's not a microquasar, but still pretty interesting. Krinkind et al. Are looking at power spectra of gamma ray light curves that they synthesized from 2D general relativistic particle and cell simulations. So even the theorists are using Stingray at this point. And Nimmo et al. Are using Stingray to look at the fast radio burst repeaters and to look at the frequency of that. So it's not just X-ray data that is being used with Stingray. But I want to talk briefly about why Stingray is being done in Python, because I know that this is not as new anymore, but it's important to motivate why we've made the choices that we have. And this is because in Python, there's this whole ecosystem of libraries and modules and tools for scientific programming. Python, first of all, is a free language, so you don't have to worry about having an institutional license to use it. Built on the basic Python language, we have the Jupyter notebooks. A lot of people find this very useful for not only exploratory data analysis, but also for teaching. You can have assignments due in Jupyter notebooks, and you can also use it as a way for students to play around with new tools. Cython is a way to wrap C code in Python, so that way you can have a numerical engine that is faster and more robust in C, but still have the benefit of the Python interface and language. And there's also NumPy, which does the basics of a lot of the mathematical tools that we use. Built on top of those, we have SciPy, which is near and dear to many of our hearts. Matplotlib, which does a lot of the plotting that we use, although there are other plotting packages as well. And Pandas is increasingly popular for doing data science type analysis. It makes it very easy and convenient to load in a variety of data sets and then do operations on them and plotting. On top of that, based on that, we have stats models, which is looking at statistics in Python. Scikit-learn is a way that you can do machine learning in Python in a very easy and straightforward way. You still need to know what you're doing, but they have a lot of documentation and tutorials to help you out. There's AstroPy, which is the key feature for us here. There's also PyMC3 for doing MCMC sampling in Python. So AstroPy is the primary reason why we chose to use Python for Stingray, because we, as Stingray, we are a AstroPy affiliated package, which means that we play very nicely with AstroPy, and we have met their standards for modern open source scientific software. So in the Stingray core library, we have a library of time series analysis methods. These are the basic things that you might want to do with a time series if you get your data from a telescope or from a simulation from a colleague. There are things like light curve manipulation and good time intervals. This can mean concatenating two light curves or splitting a light curve into two, and finding things like your basic rates and whatnot. We can do power spectra and cross spectra and bispectra, although the bispectra still needs a bit more testing. We can do lag frequency and lag energy spectra, RMS and covariance spectra, though again, this could use a bit more testing, coherence and cross correlations, phase resolve spectroscopy of QPOs, which is what I've been working on, and pulsation searches for X-ray pulsars. On top of that, we also have simulation tools. These include Timmer-Koenig power spectra. So if you define the shape of your power spectrum, what would your light curve look like? I'll talk about that in another slide. Looking at pulsations, can you insert a pulsation into a light curve and see how well you can detect it with your statistics? And looking at impulse response and 2D transfer functions, particularly if you want to look at energy-dependent lags, for example. And on top of that, we also have modeling tools. So combining the data analysis and the simulation tools. So with power spectra and co-spectra, we can look at pulsations and QPOs and noise and fit these. This is built on SciPy and MC, and it includes Laplace distributions for co-spectra. Daniela Hopenkoten and Matteo Becchetti wrote a pair of papers in 2018 with a lot more details about this. And also we're integrating with AstroPy modeling, so that way you have the benefit of the entire AstroPy modeling library without having to rewrite things into Stingray. We also have a interface for Bayesian parameter estimation and maximum likelihood fitting. So these are the basics of the Stingray core library, and I'm going to talk very briefly and show examples of some of these different tools. So power spectral periodograms, near and dear to everybody's hearts, informs at which frequencies the light curve is varying. These are plots courtesy of McKinley-Brumback, looking at SMC-X1. So we have our light curve on the left side, and on the right side, we have our co-spectrum or cross power spectrum in this case. And we can see very clearly that in the power spectrum, you see the very strong harmonic as well as the fundamental frequency, because we can also see this by eye in this particular light curve. We also have dynamical power spectra, which are called spectrograms in other fields. This is data that I analyzed from NICER of the black hole MAC-CJ 1631 - 479 from 2019. And so as we are doing dynamical power spectra, we have our frequency in this case along the y-axis and our elapsed time along the x-axis. The sudden jumps here are due to orbital gaps that I have collapsed down into nothing, but otherwise there would be big long gaps there. And so the sudden jumps are due to that. And what we can see is we can see part of the state transition here in the dynamical power spectrum, where there is nothing really happening in the time series at the beginning. And then as we transition into the hard intermediate and intermediate states, a type C QPO is appearing at about 1, 2, 3, 4, 5-ish hertz, and it has a harmonic at around 10 hertz. And so looking at the dynamical power spectrum, we are able to kind of trace and see how this QPO is changing in frequency throughout time as the source is moving through its state. One of the useful things that we have is co-spectra. So this is one way that you can do more rapid timing, getting around the timing systematics in NuStar. The co-spectrum is the real part of the cross spectrum, but the cross spectrum and all of its products like the co-spectra are used extensively in spectral timing analysis. So on the left, we are looking at, excuse me, on the left, we are looking at what a power spectrum would look like for a given source. And on the right, we have what the co-spectrum would look like. And you can see that the signal that we are looking at 200 hertz is much more clear. And we don't have all of these extra systematics when we're looking at the co-spectrum here on the right. There's also a really wonderful paper, again, by Matteo Becchetti and Daniela Hoppenkotten, 2018, looking at the statistics of the distributions of errors in the cross spectrum and co-spectrum. And so they were looking at the details of if you are able to correct for dead time in your power spectrum versus just using the co-spectrum, so using two different light curves relative to one another. You see that for the co-spectrum, the broadband noise we have down here is much weaker. This is the light pink. Compared to the two different normalized and corrected power spectra. And one of the QPOs that they have here is much stronger in the co-spectrum. So this is quite useful, and Stingray's got it. We also have RMS and covariance spectra. This is looking at the fractional variance of a light curve. So the RMS is just of one light curve, and the covariance is of one light curve with respect to a reference light curve. In the same way that power spectra and cross spectra are related to one another. So here I have a preliminary plot from one of my own papers. I'm looking at the fractional covariance of a pulsar. And so what we can see is the energy resolution of our different light curves along the x-axis. And along the y-axis, we have the fractional covariance, so the amount of variation relative in our light curve of interest here. And so these bars here are showing how wide my different light curves are. I chose quite wide ones for this one. In the energy space, and we can see that the fractional covariance of the light curve increases as we move on to higher energies. The energy resolution for RMS and covariance spectra, you have the energy resolution of the light curve energy bands that you're using. These are often binned up to be broader than the detector resolutions that you have enough counts. And full disclosure, this feature could use more testing. So if you want to work on RMS and covariance spectra, I've got a great software tool that you can try out. We also have modeling of power spectra. This one has been quite useful to one of the students I've been working with lately. So Stingray modeling has a range of statistical models from Gaussian, Poisson, chi-squared, and Laplace distributions. This is data from a paper I put out in 2018 on MaxGD 1535. And we have our QPO here fitted in the blue with a Lorentzian and the harmonic. And then we have broadband noise over here in the red. But we don't have to do just kind of this more XSpec style fitting. You can also have nice corner plots. So this is from our Stingray paper, Hoppenkotten et al. 2019. And looking at a power spectrum with some broadband noise and a QPO, you can use the corner package, which is also in Python, which incorporates nicely into Stingray. So you can look at how the different fit parameters are correlated with one another. So this is looking at, for example, the amplitude of the power law, the slope of the power law, the amplitude of the QPO, the centroid frequency of the QPO, and the width of it. So you can see how these things are correlated. And you see, for example, that the width of the QPO and the frequency of the QPO have a bit of a correlation with one another here. So this is very cool. We also have timber and cleaning simulations to simulate power spectra with very specific shapes. I know that for a lot of people who work in time series analysis, especially X-ray time series, coding up your own timber and cleaning simulation is kind of part of the PhD process. And with our timber and cleaning simulations in Stingray, you still have the flexibility of learning how it works and kind of digging into the code to see how the mathematics of it all work compared to the paper. But you don't necessarily have to do all of the code troubleshooting that often go along with writing it up yourself. So it's still a great learning tool that you can put into, for example, a Jupyter notebook. So simulate power spectra with different shapes like white noise, red noise, Bragg noise, different types of QPOs. And you can also use this in the simulation and modeling tools to estimate errors on your power spectra if it's not already clear from the data. As a general warning for all timber and cleaning simulations, not just the ones in Stingray, this does not preserve the energy-dependent phase relationships, which are often very interesting for QPOs, as you've been learning, for example, though using different energy channels are supported in Stingray. So here we have two sample light curves with different power spectral shapes. And I also want to point out, we have more sophisticated simulation tools as well with things like impulse response functions, and these do preserve the energy phase relations. But Stingray is just one part of our whole ecosystem that we have. We also have Hendrix. Hendrix is led by Matteo Becchetti, and it is an evolution of the MultPint software, which was initially written for analysis of new star timing data. So Hendrix is a data reduction interface for the command line shell and a way of doing more interactive plotting and visualizations, but also analysis tools and data exploration on the command line. Hendrix is currently in version 6.0. And I've just done a screen capture here of what the primary documentation page looks like. So you can see there are some notes on how to incorporate Hendrix with F tools, how you might want to incorporate it or compare it with the PowSpec tool. And there are also some different paper references that we have here, because one of the important things for Stingray is not only documenting and referencing what the code does, but what scientific papers this relates to. Again, this is very helpful for students as they're learning how to do analysis and learning the ropes. Hendrix also have their own set of tutorials. I am not going to leave this up for everybody to read, but just know that on the Hendrix documentation, there are extensive tutorials for how to use the different tools, such as data exploration, an example of looking at baseline flux with AGN, looking at pulsation searches. I know this is used quite a lot for Hendrix. And then just some basic things like calibrating events lists and producing light curves and loading data in. One of the really cool tools I wanted to highlight in Hendrix, this is a plot from our Stingray paper, Hope and Cote et al. 2019, is these interactive phasiograms. So looking at how the phases of your pulsar are changing in time. And what I want to highlight here is that there has been significant efforts made to integrate this into pulsar timing software like PINT or Tempo2. So the times of arrival that you get from Hendrix and using Stingray as the base can then be exported to use with other more niche pulsar timing software. So playing together nicely with other Python tools is one of the important parts.
Abby, you have about 5 minutes left.
Thanks, John. The final part of the Stingray ecosystem is DAVE. DAVE is the data analysis for variable events. And this is a graphical user interface for exploration and interactive data analysis. This is again built on top of the Stingray core library and the Hendrix command line tools. So this is a screen capture of what one of the windows might look like. So you could load up your data of your power spectrum in blue here. And then as you want to add different power laws models to fit in your power spectrum, if you had a QPO, you could add in a Lorentzian. You can actually interact with it and type in the different numbers. So for example, this might be useful for a student who's not yet comfortable with programming, with writing up their own software and importing the Stingray package or typing in at the command line. This is a great way to do just kind of quick interactive data analysis. We also have this much more complicated looking picture. This is again from our Stingray paper, Hupp and Coaten et al. 2019. And this is looking at a more detailed interface for exploring an X-ray pulsar, Hercules X1. So we have the light curve up in the top left here. And we have the average power spectrum of that in the top right. And then along the primary lower window, we have the dynamical power spectrum. And as you want to fit different models to it, you can pull these up on the left-hand window. And then you can get all kinds of FITS event information down at the bottom window here. So there's a lot of cool interactive stuff you can do with Dave. For all of this, we have documentation. So this is our primary documentation page on how to install Stingray. The two kind of stable ways to install it are via Conda or via pip. Which are very straightforward, as you can see with the lines here. There's also a way to install kind of the bleeding edge version from our GitHub, which we have all the instructions for if you were to keep scrolling on this website. So our documentation page is pretty well maintained. And we also have Jupyter Notebook tutorials. So this is teaching you not only how to use the Stingray tools, but why you might want to do that analysis and in what astrophysical applications something like a power spectrum versus a co-spectrum would be useful. So we have an entire section on notebook tutorials. We would love for you to be getting involved with Stingray. This is the page of the Stingray library code repository. And what I want to highlight is the issues page and the pull requests. Opening an issue is not like a rude thing for those unfamiliar with the GitHub interface. This is more of like a bug report for us. So if you're trying to do something and you're getting an error that you don't expect, talking about it with us. We also have a Slack workspace for discussing features and troubleshooting, but talking about it on the issues page. And then if you have code you want to contribute, which we very much welcome, the pull request page is where you can do this. This is all community developed and community run. And so we very, very much welcome input from all of you, the community. Briefly, in my last few minutes, I want to talk about facilitating astronomy research software beyond just Stingray. Some of the tools that we have for this in astronomy are conferences, for example, the Python and Astronomy Conference Series, Astro Hack Week, and Dot Astronomy. We also sometimes have special sessions at large symposia, and then there's hack days at AAS and EWAS. Hacking here is not like hacking into the government, but it's like hacking things together. So this is kind of quick and dirty software development for some cool problem that you have on your mind. It's all legal, don't worry. For training, for training people to go into to develop good sound software practices, there are the software carpentry and data carpentry workshops. I highly recommend these. I took software carpentry as a master's student. It was great. There are also paid summer internships via Google Summer of Code. We have had the benefit of Google Summer of Code students for Stingray for quite a few summers. It's paid for by Google. And there's also the LSST Corporation Data Science Fellowship Program, which I have gotten to lecture at a few summers ago. And this is a great way to train graduate students in research software in astrostatistics and working with big data in the astronomical sense. There's then databases and affiliations like the Astrophysical Source Code Library, ASCL, and the AstroPy affiliated packages. Stingray is one of them, but there are many of these, and we all follow best practices for open source research software. If what you want isn't already out there, I wanted to put together a list of kind of the basic requirements for what we've used in Stingray, but please look first to see if what you want is out there or not, or if you could just contribute to that, because there's no need to reinvent the wheel. But best practices for software include open source with version control and licensed. This is not giving up your copyright, but this is just allowing other people to use the code. Documentation on both how to implement the code and what the physics is, so citing papers in the documentation, using tutorials with examples of standard use cases, able to be imported into existing codes in Python, or using a Python wrapper around C or Fortran. This means like at the top of your Python software, you could write like from Stingray, import stingray.modeling, for example. Able to run on a standard.
Abby, you're going slightly into your question time, so I think
this is my last slide.
You're wrapping up.
Yeah.
Okay, great.
Able to run on a standard or nice desktop computer, so we don't need to run on GPUs to run the analysis, and plausible that a sysadmin will install the necessary dependencies so that you can run it on your university compute cluster. And of course, accompanying paper for proper citation and credit. So here are my summaries. Stingray is a tool for timing and spectral timing analysis. The install instructions are in our documentation page, and we have code and tutorials on our GitHub. Our papers for it are published in AppJ and JOSS, the Journal of Open Source Software. And please overall cite scientific papers in your code documentation and provide a paper so that you can get credit for your work. And software is vital for the future of astronomy. Thank you very much.
All right, yay, thank you, Abby.
Thanks.
All right, let's see, there are a couple questions on Slack. Let me read that first and then we can go to other places.
Yeah.
So, okay, so Gurno Mayer asks, any reasons why Stingray is limited to X-ray data? I guess it can also be used for high energy data.
It is not limited to X-ray data. That is what we initially wrote it for, because that is what Daniela, Matteo, and myself work on. But Stingray has been used on radio data. It has been used on optical. It has been used on sub-millimeter data. So as long as you know the statistical distributions for your data, for example, if you're Gaussian or Poissonian distributed, following the outlines in the documentation can tell you what tools you can be using, and it is not limited to X-ray data. Thank you for asking for clarification.
Mm-hmm. Okay. Are there questions in the conference room?
Yeah, yes, there is a question, yes.
Okay, we'll go there next.
Hi, Andres Gurpide here. I was wondering, I never know how to properly deal with, light curves in reality have some gaps due to good time intervals. So whether you could comment, how do you deal with that when building even the most basic things like power spectrum or?
If you have gappy data?
Yeah.
So Stingray handles good time intervals where you can define where you don't have gaps. And it takes the good time intervals into account as you want to look at your very basic kind of light curve manipulation. And then as you compute your power spectrum or your co-spectrum, Stingray takes the, if you set the flag to use the good time intervals, it'll take that into account. So we know that data are not perfect and that data have gaps. And so we have done our best to incorporate this at a very basic level.
Okay, next question in the conference room.
Yeah, actually, I have a question. Perhaps you said so, Pierre Petrucci. How many people are working on Stingray? Or it's certainly a collaboration, but
yes.
What are the
So
leaders?
the lead, yeah. So the leads are Daniela Hopenkoten, Matteo Becchetti, who you will know, myself, Paul Baum, and Simone Migliari. But we have had a lot of Google Summer of Code students over the years. I want to say on the order of 10 to 15 Google Summer of Code students. We also have other colleagues who've been contributing, like Evandro Ribeiro Martinez. Yeah, so a lot of these people are co-authors on our Stingray paper, which is right here. It is certainly more than just kind of the leads, but it is not as large as, say, AstroPi. We very much welcome more contributions. We have a lot of people who have not necessarily contributed code, but are active users and are helping us with a lot of troubleshooting and bug fixing and feature development. And so that they will eventually become code contributors as well. And we also know that having a robust kind of open source software program, contributing code isn't always the only thing you have to do to be a part of the collaboration. So for example, I don't contribute code very much anymore, but I do help with code reviews and I do a lot of the evangelizing about Stingray, for example, here. So there are lots of ways you can contribute to Stingray if you're interested.
Okay, we're running out of time, but I'm going to see if I can get to at least one more question here on Slack. So Hemanth asks, does Stingray, Hendrix, or Dave have the provision to generate GTI files for phase resolved data products generation?
I think we are able to generate GTIs. You would have to check the documentation. I always have GTIs that come to me from the spacecraft. So I would check the documentation on that. I think you are able to define your own GTIs if you would like to.
Okay. And then the second question is that when you're making a power spectrum in the leaky normalization, what are the considerations for selecting the power law normalization? I think the question is about the Poisson level. Are you familiar with that?
Yeah. With the in a leaky normalized power spectrum, the white noise level is 2.
Right.
So you can fix that if you want to, or you can allow it to fit. If, for example, you don't know how much dead time you have, dead time causes a deviation from the expected calculated white noise level. So you can freeze it, or you can allow it to be free or within a range.
Right. Good. Okay. Was there one more question in the conference room?
No?
Okay, great. I think we'll
I'll
move
be on
on.
Slack also to answer questions. Thanks, everyone.
Let's thank the speaker again.